talk about that after.
Oh, I don't know. You decide.
I can see that one from where I sit.
Maybe 1 minute? I
Yeah.
don't know. It's up to you. Shall we go?
Okay, so our next speaker is going to be Jerome Davon from the University of California, and he's going to be speaking on convex finite-dimensional variational methods in imaging sciences and Hamilton-Jacobi equations.
Okay. Thank you very much for the introduction, and thank you for inviting me. So this talk will be about optimization of convex model in finite dimension, and I will make some connection with some PDEs. So let me start with a very basic motivation and questions. Assume that you give me an image, it could be a signal, whatever, and I have a method, and in my method I have a parameter. Let's assume that it is a button. You give me this image, I turn a little bit the button, and I get an output. So here I want to filter it. What I can do is to turn a little bit more the button, and I simplify more my image. I can do that for another image. So the baboon, a filtered version. I can turn the button, and I get this result. And now the question is, if you give me an input and I turn my button, then I observe different images, and I want to know, I would like to be able to predict how from this I can go to here and to here. What is the relationships between all those images as the button is turning? And I can do that for any images. I can do also something different. I can keep the button fixed, and I can change the image over the time. So here I have two images. I take the convex combination, a convex combination, I get a result. Another convex combination, I get another result. So again, I would like to be able to describe the behavior when the images are moving. So globally, and very formally, you give me a signal, you have the parameter, and I get an output. And I would like to be able to study this mapping. So you have several questions that you would like to answer by studying this mapping. You could have a functional analysis point of view, in which space this mapping lives. You would like to get something like sensitivity, robustness. If I change a little bit the data or turn the button, how the output will react. And if we are able to answer that kind of question, then we hope that if we have a knowledge here, then we'll be able to design better algorithms. The original questions, I am a computer scientist, and I focus on designing efficient algorithms for doing optimization. And over the years, then you realize that it's very important to be able to know how the solution will react to smaller perturbation, so that you can tell the algorithm how to compute more efficiently. So that's the idea. Okay, so still again, non-rigorously, I'm going to assume that I have a true image, U bar. So this is a true image. Then I can see it through a linear operator, A. Then eta is some perturbation. You can see it as a noise, so a perturbation, and I observe X. So now you give me X, and the goal is to recover the true signal. In this talk, I only consider finite dimension framework. So it means everything lives in Rn. What I observe, what I plan to recover, and the perturbation. So in order to do the analysis, I assume that you can observe any kind of images. So you can observe possibly any kind of images. It means this spans Rn. So now what it says if you give me an x, then I want to be able to get a u. Otherwise, if you do not have that assumption, then the analysis can be complicated. In this talk, I will assume that this linear operator here, it will be a matrix, is invertible. And I won't talk about when A is non-invertible. We did some work with Stanosha, but we won't talk about that. And to do that kind of work construction, I will focus on variational methods. If you are doing Bayesian methods, then it is the maximum a posteriori MAP estimator. It's the same thing. Okay. So the outline is pretty straightforward. We'll talk about first the energy of the variational method and then the minimizer. Okay. So let's take an example. Assume that you have a Gaussian additive noise. So this is the model of your for your imaging. Then the Gaussian term will become quadratic data fidelity. T is the button you turn that corresponds to the amount of noise you believe you have in the image. And then you add a regularization term, a priori term. It could be your favorite one, TV, L1, whatever. And X is your observed data, and you minimize for Y. So I give here several examples. If you assume that your signal is sparse, then one common prior is to consider L1. If you assume that your signal is piecewise constant, then it could be that kind of total variation. You can define other kind of total variation, like the little L2, to get more isotropic version of TV. It could be non-local, and you can put any kind of convex function that you want here. For instance, the Hubbard function. All I'm doing here works for all that kind of priors. So there are two quantities of interest. The minimal energy. You give me the data, you give me the parameter, I optimize for Y, and I get back the minimal value. So in the literature, you call that the Morrow regularization of the prior, G. It could be also called the Morrow envelope. And this is a well-valued function. But in signal processing, then you are interested not in this minimal value, but in the minimizer. And when you have something quadratic like that, then in the literature, you call that the proximal point of X relatively to the prior, J. So I want to study those two mappings, and in particular this one, which is of interest in imaging. So again, let's try to do some experiments with that. So here I consider a discrete version of total variation. It is the anisotropic version. We have algorithm to solve that exactly. So you get Y, the exact solution Y without any error. And I plot, maybe you don't see it. No, you don't see it, okay. I plot the energy as T is increasing. I fix X and T, and I observe that kind of curves, convex curves. So this is what we have here. The energy seems to be convex. I did that for my convex combination, and again, the plot of the energy is convex. So, yeah, exactly. It's the baboon, and this is an aerial view of Montpellier. And it's 0.4 and 0.6. It's only a toy example, right? I mean, we're not doing image processing. It's simply for illustration. So again, you observe something that is convex. Okay. So essentially, the first thing that you want to prove is that this mapping is convex. And I'm going to study it. So in order to study that, I need everything will rely on convex analysis. Everything. So we need some definitions, but it's quite common in convex analysis. So the convex function you're working with are proper, so it means it has to take finite value somewhere. They are lower semi-continuous, and they are convex. So this is the nice class of function that you want to work with. Then we need to define, to generalize the notion of a differential, because we want to be able to tackle convex energies or convex priors that are not differentiable. And you introduce the notion of subdifferential. Essentially, it's okay, let me do an example for L1. For the absolute value. At 0, it will be either linear support, linear form that will support the function at this point. If you are differentiable, then the subdifferential has only one element, it's the gradient. So it's all possible generalized gradient that you could consider. So if you give me a vector of the subdifferential, then this is what we call the gradient. A very useful transform in convex analysis is the Fenchel-Lechon transform that is defined by this formula. And why is it so important? Maybe it's because of this property. If you give me an element, a subgradient of f at x, then you get that property in terms of the Fenchel transform. So in other way, instead of seeing the function, of representing the function at, you give me x and I associate the value f of x, it will be you give me a subgradient and I tell you every x that are admissible. So it's another way of representing the function through the derivatives, essentially. And one way to generate convex function is through the infimum convolution. So among, you have x, and then you can split x into two parts so that you minimize this energy. Here you can think about, if you have an electrical system and you think about the energy, you put, you have two resistors, you put them in parallel, and then the current will flow so that the energy will be minimized. And then you can generalize that to any convex function. And if this infimum is attained, then we say the infimum convolution is exact and the infimum is a mean. And we will be always in that case for the analysis. So basically this is what you need to understand the convex optimization problems we are dealing with. So here is an abstract formulation of what I consider an imaging problem. It is the infimum convolution between J, that will be a prior, and this will be my data fidelity. Let me give right now an example of H star. If I take H to be quadratic, then this will be also H star of x. So if I plug that here, then you get 1 over 2t x minus y plus j of y. So this is the Moreau envelope of j. In order to be able to do the analysis, okay, we will call that if you give me x, I always want to be able to find a solution. So I want the existence and the uniqueness of solutions. So I'm going to add some assumptions on those quantities. Okay, there are two sets of assumptions. Here, what I'm saying is that it's a lot of assumptions. They are rather natural. Essentially, it says the following. It's this problem will always have a solution. What? A? No. No, it's hidden in the H star.
Oh, okay.
Okay. It's saying that with that kind of assumption, then you have the existence, you have the uniqueness, and you have additional properties that will allow me to make the connection with Hamilton-Jacobi. The thing is, if you remove one of them, then the whole strategy for doing the analysis will collapse. So you have two sets of assumptions. Essentially, I do that to consider two cases. Either the prior can have some constraints. For instance, you say, I want to find an image that is non-negative. And you're going to put this constraint into J. And then that induce some consequences on the data fidelity. Or you can do the opposite. If I assume that the noise of the perturbation is bounded, then I have to assume that the prior allows all possible images. So it's two scenarios. Either you assume that the original image lives in a subset of Rn, or you assume that the noise is bounded. Okay. So now we can go to Hamilton-Jacobi equations. So Hamilton-Jacobi equations with initial value takes the following form. So what you're looking for here is the function E. Then this notation here denotes the spatial gradient. H is called the Hamiltonian. In general, you cannot hope for classical solution. Classical in the sense that the gradient of E will not exist everywhere in the interior of the domain. It's most probably you won't have that. So that's why those guys, famous guys, came with the notion of viscosity solution. It turns out that with the previous assumptions, all the solutions will be classical. So we don't need viscosity solution. And we have a representation formula under the assumption that J is convex, H is convex, and the previous technical ones. So there is a unique differentiable and convex function that takes the following form. So that was done by Hopf, I think in the 50s. Hopf lacks a little bit later in a different context. And this is the infimum convolution. Essentially, it says, in order to solve Hamilton-Jacobi equation, then you only need to compute an infimum convolution. The infimum here is attained, so the infimal convolution is exact. Because it's an half convolution between two convex functions, E is convex in both variables, that I explained why we observed convex energies before. And you have a pointwise limit. You can have a stronger convergence, but that's enough for what we are dealing with. So the thing is, you only need to observe that the solution of the Hamilton-Jacobi equation is exactly the quantity of my image processing problem. It's a simple observation. So what you do is the prior becomes the initial datum of Hamilton-Jacobi, and then the data fidelity defines the Hamiltonian. I guess so. If I'm really eager to know if that happened before. I don't know. Stanhope didn't know. Chambal didn't know. Many old people I talked didn't know. It's a simple observation. So again, it's very structural. Okay. So blue, blue, red, red. That's it. So the thing is, what Stanhope showed on me that it's kind of crazy Hamilton-Jacobi equation because of the initial data. He said, people generally do not think with that kind of initial data in so many dimensions. Because here the dimension is n, and n is the number of pixels. So we're talking about several hundred thousands or millions. And you want to solve that kind of stuff, very high dimension. And something, again, just by the observation, is that if you want to evaluate the solution at a given point, then this is what we do in image processing all day. You can use your favorite algorithm, and then you get the value of the Hamilton-Jacobi equation at one point. So let's take examples. Well, here I only consider the E, but the algorithms are computing the U, I mean the minimizer. But if you have the minimizer, then you get the U. Yes. So a simple example, I mean the simplest example, again, H is quadratic. So this is your Hamilton-Jacobi equation. So you get that kind of problem. So it's your typical quadratic data fidelity plus the prior, so it's Gaussian additive noise. If you consider the prior TV, then you get exactly Rodino-Shofratemi. And here in this setting, then you can impose some constraint on the image you are looking for. And it still satisfies, I mean, you still have this equation and this solution. So here you have the A. So my A, again, is positive definite and invertible. Then you plug that in Hamilton-Jacobi. You compute your Fenchel transform, and if you evaluate at the good data, then you get a deconvolution problem, again with a Gaussian noise. We can deal with other kind of noise. So you take a Hamiltonian of the form of a convex function of any norm. Then you have that kind of nice formula, and you can do that for LP norm, and then you get that the data fidelity will be Q. I mean, if you give me LP, a P, then you get the conjugate, and then you get the power to the Q. So you deal with a general Gaussian noise distribution just the same way. Here, it's an example where you assume that the perturbation will be bounded. So the idea is that you take the Hamiltonian that you use in special relativity. So 1 will be the speed of light. Here we say it's 1. You compute the Fenchel transform, and you get that kind of model for the noise. It's only an example. Okay. So the connection is very, straightforward. How the minimal values of your convex optimization problem is related to Hamilton-Jacobi equations. Now we want to know the behavior of the minimizer. So the minimizer, again, Hamilton-Jacobi, the solution of Hamilton-Jacobi, and the minimizer, it's unique and it exists. I call it U. So you give me the data X, you give me the smoothing parameter T, and I get the minimizer. So this is the mapping of interest now. Okay. Whoops. Yeah, okay. So let's try to understand what's going on again, an example. So again, the Hamiltonian is quadratic, and my initial data is L1. So it means Gaussian noise, and the prior is L1. So the Hopflachs formula yields this form, which is used in many, many places and many, many papers. This is what we call, the solution is given by a soft thresholding, or Stan-Osher call that shrink. I don't know why, but it's soft thresholding. And so U is given pointwise by applying this operator, which is, it's pretty simple. If you are above A, then you reduce by alpha, and so on. And if you are between alpha and minus alpha, then you set to 0. It's like a wavelet, soft thresholding used in wavelets. But we don't, okay. It's not nice. It's nice to compute, but then we we want to have a better idea of what's going on. What is the impact of the prior? How the Hamiltonian and the prior interact to give this formula? So we work a bit more, and you can reformulate this only using a projection. So what I'm saying is that the soft thresholding is simply x minus the projection of x, so on this convex set, dilated by t, and you compute this difference. You work a little bit more to express this expression, and you get this form. So you have that the minimizer is given by what you observe minus t and some quantity here. That is an element of that. So that problem has been, I mean, it's in this paper of Buddy and Osher, they give lots of more details about this problem. But let me generalize it so that I get to my point. I'm going to replace L1 by a general one-homogeneous convex function. It could be TV, it could be L1 or whatever. So you can apply the same strategy where C, so again, you're going to get the projection and the same kind of formula. And what is C? C is the subdifferential of your prior evaluated at 0. This is where everything is important. And so what you see here is that that element here is related to the prior, J. And you could study that mapping through the stability of the Euclidean projection onto convex set, but that would work only for one homogeneous function, so we want to get now the general idea. So I want to get back an idea that what I'm looking for is my observed data minus t. You can think of some time, and this will be somehow some kind of speed or momentum. And the momentum will be related to the prior. So let's do that. So again, Hamilton-Jacobi, the solution of Hamilton-Jacobi, and I want to take the subdifferential for the variable x when t is fixed. So this is what I do here. T is fixed, and I want to compute the subdifferential of this quantity. Using convex analysis, when you have an infimum convolution, then you take the subgradient of your two terms, you evaluate them at the minimizer, and you take the intersection. So this formula is very nice. I mean, it's a simple formula for something complicated. So now we want to see in details, what is this quantity? Well, so we have it here. You can easily prove that the subdifferential of the Fenchel transform of the Hamiltonian is actually reduced to a single element. It is differentiable. So this contains only one element. So now I'm going to take the intersection between a set that has only one element and this one, and I have to check that it is not 0. The empty set. If it's empty, then that would be okay, no subgradient. So again, it's very easy to prove that. So actually, you have that E is differentiable with respect to the spatial variable, and you have this formula. So again, I have my formula for the spatial derivative. And then you have, using the Fenchel transform property, if you want to invert the differential, then the differential of the Fenchel transform is the inverse of the differential of H. This is a very nice, I mean, that's why we are using the Fenchel transform every day in convex analysis. If you wouldn't have that, then we couldn't do much. So then you get that formula for the minimizer. It's explicit. So U, the minimizer, is given by X minus T, and this quantity, so that involves the gradient of E and the gradient of H. So it's an explicit formula. I forgot to say, if you are familiar in physics, E is what we call the action. This is in the action, and J would be the initial action. Then you can differentiate with respect to X, and then you get the conservation law, and then the initial data will be the initial momentum. I forgot to say that, sorry. So we got our formula, but it's only valid when T is strictly, is positive. So now I want to see the behavior of the minimizer when T is going to 0. Why I want to do that? It makes me think to when you have a semi-group, then you want the generator. You want to know in the image processing point of view what's going on for very small regularization. Because if the result is not good for small one, then there is no way on hope that for bigger one, for bigger T, it will be good. So I was interested a lot into that. And how are we going to do that? Well, I'm going to take my sequence of smoothing parameter, and so I turn the button back to 0. Then I'm going to consider sequence D that is converging to D. And I'm going to approach x0, the point of interest, along the direction D1. So here I can draw a simple thing. If you have your point of interest and a direction like that, then you approach your point for any kind of direction, and you allow that. Why you want to do that? Because assume that X lives in a constraint, and the only way to approach it correctly is using a convergence using direction. Otherwise, if I am here and I take this direction, I am outside my sets, and nothing makes sense. So that's why we're dealing with that kind of convergence. And so we want to analyze what's going on for the minimizers, what we call the semi-derivative. So it's the variation of E, the empirical derivative, and the gradient. Okay. So I have my mapping, and you get something that you really want to have that. It says, when you approach the data X and you turn the regularization to 0 at the same time, then you get back the data. So you simply say that when you have your variational method and you turn the button back to 0, then it's saying that you assume that there is no noise. This is something natural. So we have it. Now what about these quantities, the gradient? So here we have to consider points where the subgradient is not empty. Otherwise, this does not hold. So you can show that this sequence is bounded and that any accumulation point of this sequence lives in the subgradient of the prior evaluated at what you observe. So these are essentially technical results for the formula that we have. So we have explicit formula for the semi-derivative. So you have this form, and the sequence of the special derivative is essentially the same one, but you take the arg maximum. So here what you get is that you have that those two quantities, the variation of E and how the gradient is moving, is exactly the maximum deviation between this linear form. So you give me the direction D. It depends how you approach your data X. It depends on the direction, how you're going to approach. And your Hamiltonian. And you only look at that only where for the element of the subdifferential of J. So that tells you what is the impact of the prior. If you take something that is completely differentiable, then this is only one element, and so then this is there is no flexibility. So that gives a way, I think, to tackle how things will happen in image processing when you want to know what's going on for the small perturbation, or if this prior is good for you or not. For instance, for TV or for any kind of convex prior, then you will have the loss of contrast. So it's not only TV, it will be anyone. So then most probably, it's not most probably, the shape of what you observe will tell you the speed at which you lose the contrast. And so you can get a precise analysis of that kind of behavior using that kind of formula. Okay. And so, okay, is it that new? Well, yes and no. Because if you take this, okay, this is the formula for the special derivative of E. You take quadratic Hamiltonian, you fix the image, and you consider this mapping. If you write down the formula, then you open your book of functional analysis, then this is what we call the Yosida approximation of the subdifferential of J. Here you could even replace that by any maximal monotone operator. So if you apply this formula for the direction 0, 1, so it means x is not moving, so I stay at x, and only the smoothing parameter is going to 0, then you get this result. And this is super well known, at least in differential inclusion literature and contraction semigroups. That formula, is very well known. So it's only, so in that sense, when I see that, then I say this formula is only a tiny improvement compared to this. This is a huge business, I guess in the 60s and 70s, to give sense to what we call the differential inclusion. So you have du dt, evaluated at t, let's say minus j of ut, and you have u0 equals u0 somewhere. So you want to find a function where for each t you associate an element that leaves for any t in the subdifferential of j. So one way, so you may have many solutions, but if you look for an absolutely continuous function, then there is only one. And the way to compute it, to define it, is exactly minus projection of this. So you say, how do you select? You see that as a set of possible speeds. You say nature is lazy. I don't want to move. If I can choose, then I choose the speed that is minimal. So you pick this vector, and then this is how you, now you have your ODE, you solve it, and this is solution of this one. So that's why people have been doing that a lot. So another way, the other words is what we call the resolvent and stuff like that. It's all related. Okay, I went a bit fast. Okay, the idea is that we can relate convex optimization problems in finite dimension to Hamilton-Jacobi equations. So you can use your favorite algorithms to evaluate the solution of some specific Hamilton-Jacobi equations. We have formula to describe how the energy is moving, how the minimizers are moving. You can extend that to, I did only for real valued images, but you can extend that to vectors or colors or hyperspectral. It's simply a matter of how you put things in the vectors. You can use more sophisticated convex model, like for instance the nuclear norm and stuff like that. And with Stan-Osher, we did some work on the case where A is non-invertible, with L1 prior, typically a compressive sensing-like problem. And I don't know, I think we need to work more on that. It's not clear yet. I think I should stop here. Thank you.
Flow. Because it's a flow for all images actually.
Yep. It's crazy.
It's not something that you would use numerically.
No. Yes, okay. So when, okay. No, I think everybody is asking the question. I would love to use that. I just don't know how to use it yet. Because you have a formula, okay. My guess is the following. When you go to those combinatorial methods to solve TV problems, like a graph cut, then, I'm very familiar with that. The thing is, you have a big graph and you have 2 points, and you need to find a path that is joining these 2 points. When you apply a perturbation, all the algorithms I know are just blind. They just restart as if they did nothing before. That kind of formula, I think, would be helpful, but so far, I do not have the algorithm, but I think I'm close. But other than that, let me tell you, yeah. If you look at the flow, okay, you give me x, and you start from t equals 0 and try to increase t and to follow the trajectory, then the performance of the algorithms are not good. I tried that. Following this flow doesn't give a fast algorithm. So.
The follow-up is that usually when you have a flow, you can start from a certain time.
Yes.
It's not the case here. You cannot go to a certain time and initialize with the data which you have gained.
Yeah, no, you can do that because this is Hamilton-Jacobi, so you have the semi-group. So you can solve for a small time, then you get your solution. You could estimate the gradient, make a prediction, and then we start again. Does that make sense?
This is what I would have expected, but then you would have to see it in the energy function as well.
Yeah, but you have the gradient. You have where is it? The gradient. You have it here. If I know u, the minimizer, I compute this difference, and if I know how to evaluate the gradient of h star, then I know how to evaluate this quantity super easily. It's only the difference between observed and reconstruction. So if I know how to optimize for some time, then I know how to evaluate this quantity super easily, and I just apply this operator. If it's, for instance, quadratic, then it's identity, and that's it. So you know how to evaluate the gradient of E super easily.
Don't have u.
If you have u, yeah, but yes.